Again, good morning to all. So, last time, and meron taon-taon na gito nga last time ba? We ended with the ALU, no, or ALU, or the Arithmetic Logic Unit, which forms the brains of our microprocessor or of our computer. Okay? So, any CPU, any microprocessor would not work, of course, without memories. So, sa una pa, we've already known the four main components of any computer. Computers dapat na yung mga input devices, output devices. We have the processor, and we have the memory. So generally, we have known of two types of memories. We have the random access memory and the read-only memory. So for each of those types of memories, na iyang own technologies. So for this meeting, we'll be dealing with random access memories particularly. So sequential circuits and memory. Memory within context here is random access memories. So memory devices for us, we've known memory devices to be implemented with RAM, no, or random access memories. So this is the hierarchy of the memory device, the RAM. So ang atong RAM or random access memories is basically just made up of arrays of registers. No? So I don't know if you remember or if I played the video before. I think na-play mo na ako ito, no? Katong regarding memories. And we have known na ang RAM is just made up basically, no, of arrays of registers. And registers are just made up of flip-flops, basically. So in the context of our learning microprocessors, the register here is a 16-bit register. Kani siya. Sorry. Kanina dire, no? Wala dire. So muna siya 16-bit na register. And in the same way that the RAM is made up of an array of registers, our register is made up of arrays of flip-flops. So the most basic flip-flop that we have, the most basic memory device that could store memory conceptually is our D flip-flop or data flip-flop or DFF. Do you still remember this kind of flip-flop before sa logic circuits? There are different types of flip-flops man, diba? I think there are 4 most commonly used flip-flops in logic circuits. So we have aside from the D flip-flop, which we have now, we also have the JK flip-flop, SR flip-flop, and T, or toggle flip-flop. So latches flip-flops are all synonymous device. Nalang sila yung mga mag-differ in some few aspects. Pero latches and flip-flops are basically the same. But what we're going to focus on here is just the D flip-flop. No? So in the same way that our NAND, remember ang atong pedagogy, no? Or ang atong way pag-learn is we basically just have our NAND gate, which we use to build different kinds of gates, diba? Which we use to build different kinds of chips and circuits and systems, etc. Diba? So katong atong mga, and it all went up when we built our ALU. No? So in essence, no, our ALU is just made up of a complex array of NAND gates, diba? So malaging ana. So in the same manner here, because ALU is just a purely combinational logic circuit. Combinational meaning wala siya di siya store memory, no? There's no way for it to store memory. Ang iyang counterpart ana or counterpart sa combinational logic circuit, a circuit or a logic circuit that could store memory is a sequential logic circuit, no? So basically, sequential logic circuits are, of course, made up of memory devices. And its most basic form is the D flip-flop. So we start with the D flip-flop, and then the D flip-flop is what makes our 1-bit register. No? Actually, gamay lang ang difference sa D flip-flop o 1-bit register. If you observe our simple nga visual, the 1-bit register is made up of only one D flip-flop. So, kanang 1-bit register, ato gyapon ng i-array 16 times, which will give us a 16-bit register. And atong 16-bit register will comprise or will make up our random access memory. No? So, yan na lang. Yan simplified. At least ang top level na analysis sa RAM. So in the same way that the ALU is just made up of bunch of NAND gates, the RAM is made up of D flip-flops. So what can a D flip-flop do? So before that, I think that's the next question that we need to answer. What can a D flip-flop do? Para dali ma-remember, again, D flip-flop is able, the D flip-flop is able just to store 1 bit of memory. So when we say storage or memory, in contrast to a purely combinational logic circuit, whether that combinational logic circuit is as simple as a few gates to as complex as the ALU, basically time is not a factor when it comes to combinational logic circuit. No, dili na consider ang time. So when we say time, or if a circuit considers time as its factor or parameter, it does not only have set of inputs and outputs, but it also has a specific state. So I'll just put it right here. When time is considered, it allows our circuit to have some kind of state, sa iyang present state. So naman tayo duha ka possible states actually. In the same way that our inputs and outputs has 2 types of possibilities, on and off, the same gamon sa state. A state could either be 1 or 0, the same, or on or off. Either way, wala gyapon, 1 or 0, on or off. So whatever the state is of the device, because it has a state, na siya current na state, it will be able to carry that state whenever time goes forward. Okay? So unlike the combination logic circuit, time is not of the essence, so to speak. Time doesn't matter. So the output is just a function of the input. So for the combinational logic circuit, just like the ALU, output is a function of the input. Whereas for sequential or memory devices, the output is a function of not only the input, but of also the state. Say ang current na state. Okay? So pause lang sa ako kadyo class na so ikaw. Few moments lang. Okay. So memory circuits, sequential circuits consider time. Hence, able siya maka-store og state. Hence, na siya capability to have memory. So ato sang i-analyze more, how can we quantify time in this context, no? In the context of the study of microprocessors. Okay? So maybe review the ganin if you've already covered this one last sem sa logic circuits, but if not, this is still a good review. So we have right here, okay, ang atong of course, visualize the time in terms of graphs sa atong field is moving forward, no, in that direction. Okay? So ato na siyang gina-subdivide, of course, into partitions. And then for each division is a unit of time, no? So a unit of time, actually, magdepende na sa designer, how short or long could it be. It could be 1 second, no? Pero actually sa microprocessor design, dapat ka ng 1 second. So it could either be 1 millisecond, and still that is a very large number gapon for microprocessors. Siguro 1 nanosecond is good. So it might be 1 nanosecond or 10 nanoseconds. So this is 10 nanoseconds, 10 nanoseconds, and so forth. So this is a 10, this is a 20, this is a 30. So depende, no? Depende sa designer, sa atua, how much is our unit of time. So I think it will suffice if we'll just consider this to be 1 unit of time, this to be another unit of time, another unit of time, so on and so forth. So for time to go forward, malag weird siya paminawon, wala may instance na nag-stop ang time. But para ma-visualize nato time going forward, we'll introduce something that we call a clock. A clock. Practically, no, or in actual, the circuit that we call to generate this waveform, it is called a clock. And it could manifest in many ways man, no? Pwede na siya output sa isa ka oscillator. Okay? Oscillator. And as we know from electronics 2, or even in comms, oscillator is a circuit, maybe made of crystal or made of RC circuits, or LC tank, pwede. Op-amp, pwede gihapon 555 timer, pwede gihapon, no? Pero right now, it doesn't matter to us what specific type of implementation the clock is made of. Basta kaya iyang output, it's capable of generating a sequence of on and offs. So let's just focus on the first unit of time. So it started with a low, no, and midway, tunga sa kuan, halfway sa unit of time, it will go high. So low to high. So pwede gyapon nga ang pag-design nato sa atong clock is dili mag-start ang 0, dili ang first unit, dili ang second, no? So that it will go from high to low. So pwede gyapon na siya. So arbitrary, technically it's arbitrary what we will choose for the first na instance of time. So for this lang example, our clock goes from low to high, and then low na pod to high, and then low na pod to high, so on and so forth. So to go from low to high lang, no? Dili man necessarily 0 to 1 gid ni siya. So low to high lang sana siya. Yeah. So also in logic circuits or combinational logic circuits, because time is unimportant yet, wala pa nato i-consider ang delay, the phenomenon called delay. But delay actually is a real occurrence, and it also it occurs actually in it is a great consideration in the design of microprocessors. Even simple logic circuits actually, maskin simple na ang logic circuit nga atong gibubuhat sa breadboard, ato gid consider ang delay, especially if our circuit is a sequential logic circuit. Pero kung combinational, gamay lang kaya na siya nga matter, no? Gamay ka nga matter ang delay. So, hindi kaya na siya big deal. Kung purely combinational. Pero if sequential na, no? Ang gamay nga delay sa isa nga part sa circuit that will compound manggod to other parts of the circuit, mag-carry over na sila. So, consider that to permit ang delay. No? So here, sige, before I proceed, consider this very simple na circuit. 3 NOT gates, no? Naka-series. So kani, this circuit will be able to give us, if we intend our circuit to, example, no, and a NAND gate na siya. So A, B ni dire Y. No? So what if we intend sa A nga kuan, or X lang si dire Y, if Z na lang ning output. If we want sa X na input to be much slower than sa Y, so we introduce a delay sa X na part. No? So atong gituyo nga butang delay. Pero kung combinational lang yun nga input-output atong gusto, di naman mag-matter ang delay nga kay tabo diya. Pero if ginatuyo ginato, mo delay gamay si X kaysa sa kay Y, let's say si A ug B is the same ni siya og gigikanan nga input, no? Let's just say na lang, yan na. So what if each logic gate, if not each NOT gate will be able to introduce at least 1 nanosecond of delay. So mas slower si X by 3 nanoseconds compared to Y, or mauna si Y by 3 nanoseconds compared to X. So even this simple circuit, no, very simple lang yun, tulo lang na sila ka NOT gate nga gitapad, maka-introduce na siya delay. So again, for combinational logic circuit, dili na siya matter. But for sequential logic circuits, for memory circuits, delay matters. No? So how will we solve that problem? No? So how will we mitigate that one? So pause lang sa again, class. Wait lang sa. Sorry, so I'm back. So let's say, for example, we have no? Sorry, class. Nanawag. So let's consider a particular logic gate. This one, the NOT gate. No? So if dili nato consider ang time, of course, if 1 delay sa input, 0 sa output. If 0 sa input, 1 sa output. How will that look like sa atong kuan? Time plane. So this is in, this is out. Yan na. Instantaneously, the moment mag go from low to high, ang atong input, instantaneously, ang output mag-go from, of course, high to low. But in actual, it's not like that. It's like this. Na delay. Okay? Even ang pag-go from low to high sa input, it's not as instantaneous as that. It will have a more curve na response. It will go from low to high. So the moment nag-high na siya, the moment nga ga-increase na from low to high, ga-decrease po, no? Not instantaneously, but momentarily gihapon ang ato output from high to low. No? So this is the totally high na output. This one from 0 to this point. Dire from totally low ni siya, no? So kani purely 0. From this point onwards. So kaning very special nga point here. Yeah. So dili siya totally 1, totally high, di po siya totally 0. Mo ni siya atong inatawag na delay. So this is the delay nga portion. Because even sa input na side is na ay delay. Yeah. So how will we solve this dilemma? How will we solve then this dilemma of delays? Okay, so ako nang erase because na visualize man siya properly right here. As input goes slowly from low to high, output will go slowly from high to low also. No? So kanina naka-shade og gray, muna ang delay. After sa shaded gray, defined na, no? Defined na. So clearly, this is already high ang input and ang output is already low. Okay? Clear and defined. What is not clear and not defined is the part sa delay. So how will we solve that one? Or how has designer solved that one throughout the years of designing logic circuits? So I'll put out a statement here. The cycle's length, one of the solutions to this one, no? To solve this dilemma, walang isulat. Actually, di pa dahil siya ang dilemma. Later pa ang dilemma. To solve this problem, to mitigate or solve the problem of delay, to solve the problem of delay having an effect to the overall system, no? Because if nag-delay din nga part, no, nasibog na ang atong kuan, ang atong intended na output, instead mag-start siya dire, hindi rin nag-start, no? So it will have a compounding effect sa future na response. So to solve that problem, solve problem of delay, designers has found out that the cycle's length, uh, the cycle's length must be longer, than the maximum time delay. Than time delay that can occur. That is possible. Okay, so solve this problem. The delay, the cycle's length must be longer than the maximum time of delay. Para mahimo na it will make the delay insignificant or arbitrary. No? So the cycle here, okay, meaning the 1 unit of time, if the unit of time is longer than the actual delay, it will make the delay insignificant. How? Okay, so back to this cycle. What if our cycle is, ito kung na, kung kanina, 10 nanoseconds, no? What if 10 nanoseconds ni? Okay? And the delay is only 2 nanoseconds, no? Meaning sa 8 nanoseconds after, nag sort of stabilize na ang output, right? Nag-stabilize ng output. So for these 8 nanoseconds, that is not affected by the time delay. Okay? Pwede na nato somehow model ang input-output to how we normally model it with ideal conditions, no? So delay aside, because the actual cycle is longer than the maximum delay, it made the delay arbitrary because the output already has stabilized. So pwede na nato ma-visualize or ma-model ang atong input-output as what we normally do, no? As instantaneous lines na. So pwede na yung ana. Okay? Because delay doesn't matter na as of this point. So what's the problem right here? Say problem then. On one hand, the cycle should be sufficiently long to contain and neutralize any delay. And yet on the other hand, sige daw, basig na yung makaguess sa inyo class, unsay possible na effect if we lengthen the cycle time, no? So what if ako ning needless ug butang sige para neutralize gyud na atong kuan, if 15 lang ni para sure. So unsay effect kahana class? Kasi gusto mag-guess, no? Guess lang good basi daig na mo idea. What will that create, no? What sort of problem will that create then if we just increase to a arbitrarily large value ang atong cycle, no? Siguro para sa mga computer enthusiasts here or kanang gabuild og ilang own ng mga PC basig na may idea, no? Mas ma-imagine man niyo ni more easily. Okay? Ba? Sige lang. So if wala, so yan may tabo. Again, on one hand, we would want our cycle time, our cycle unit of time to be longer than any delay, so as to neutralize any delay. Yet on the other hand, actually we want our cycle time to be faster, no? The shorter the cycle time is, the better, no? So why is that? Or how is that? If the cycle time manggod is shorter class, no, it will make ultimately our microprocessor or even this memory device to be faster. No? Mas makamake ta og more faster device if mas shorter ang atong cycle time. No? So if this is originally 10 nanoseconds, but if ikat na to siya into half, 5 seconds kibali ang clock. Okay, sorry, 5 nanoseconds kibali ang clock. So ang cycle duration is only 5 nanoseconds. So na make na to siya og 2 times faster compared sa atong 10 nanosecond na clock, no? So how about karon, pila ba ang clock sa atong mga CPU? Okay? Akong search ha. Clocks, di ba clock speed is important man for na consideration when purchasing or even building our own computer units, no? So clock speed daw of let's say i7, no? So i7 has a clock speed of 3.6 gigahertz. So how much is that in terms of nanoseconds? 1 divided by 3.6 giga is -9. Yeah. So in terms of nanosecond, okay. So if this is an i7 class, no? If this is an i7 nga microprocessor that we're talking about right now, it has a clock speed of 0.27 nanoseconds. So you get the picture, no? Compare lugar na to sa kuan, clock speed of i7 na siya. Karon, no? Karon nga microprocessor. Pentium 4 daw, be? Pentium 4 has a clock speed of mga 1.3 gigahertz. So 1.3 gigahertz is 1 divided by 1.3 giga. So nano 0.77. 0.77 nanoseconds. Tapos mas gyapon compared sa mga primitive na microprocessors. Ang Pentium 4 is 0.77. Ang i7 is 0.27. So pila na siya? How much times faster na siya? 0.27 divided by 0.77. So 0.35 times faster than i7. So the point is, the shorter, no? The shorter, ang ato biyang intent is we want our clock speed or our cycle to be longer so as to neutralize delay. But we want also our cycle to be shorter because the shorter the cycle duration, the faster the computing speed is, no? So that there is the dilemma actually. So mo tong dilemma. On one hand, the cycle should be long to contain and neutralize any possible delay. On the other hand, the shorter the cycle, because di man pwede long ang cycle sa atong memory, then short ang sa atong processor, no? So dili sila mag-coincide. So on the other hand, the shorter the cycle, the faster the computer. Okay? If things happen only during cycle transitions, then obviously things happen faster when the cycles are shorter. So to sum up, the cycle length is chosen to be slightly longer than the maximal time delay in any chip in the system. So here's the dilemma. No? So to solve the problem of delay, the cycle's length must be longer than the maximum time delay. And on the other hand, the shorter the cycle time, the faster the computer. So this is the ideal nga So ang first na to i-determine is how, of course, the first thing you determine if ever you'd become microprocessor or chip designers is based on whatever technology your chip is made of, no, whatever semiconductor technology it is made of. You must determine the delay time, no, the maximum delay time, this one, and make the cycle time just slightly longer than that. So if mo consider tatong 0.27 nanoseconds or 270, okay, 270 picoseconds, then fraction lang ana dapat ang delay, no? So maybe, no, maybe 10 picoseconds ang delay sa atong sa atong, if 10 pic, no, sorry, kasi gamay na po ka ng 10 picoseconds. No, let's just say if 250, no, or 200 picoseconds ang atong delay, so I think that's good enough, no. Pwede na siguro nga 70 picoseconds ang time niya to stabilize. Basta kay the point is the cycle time, the cycle time could possibly be just a little slightly longer than the maximum possible delay. Okay. So that's for consider the quantifying, timing, and delays for sequential circuits. So let's move to the very first and most primitive memory device or sequential circuit, the D flip-flop or the data flip-flop. So how does this work? Before I go further, we should note that for any memory circuit or device na lang, for any memory device or sequential circuit, okay. So for any memory device or sequential circuit to be called as such, for it to be able to store a state, it must have at least one data flip-flop, no? At least one lang, to introduce the notion of state storage. Okay. So siya ang mag-introduce o delay, siya ang mag-introduce o capability to store the state. So how does the data flip-flop work? So muna yung specs, no, na right here sa upper right portion. Yung function is the output at any instance of time one step forward or one cycle after is a function of the input or the present state of the input. No? So input at time t is equal to the output at time t plus 1. No? Okay, kung purely combinational siya, ano naman na output at t. No? So the input now, the output later is the function of the input now. No? It's either the input now is ang output of function later, or the output now is a function of the input earlier or previously. No? Either way. So pwede ang now is ang t plus 1, meaning ang t is kanina, no, or earlier. Or ang if now is ang t, later ang t plus 1. So this is the function, no, or the response of the data flip-flop. Very simple. iyang present iyang present na output is the previous na state. So consider at cycle 1. So dili lang sa cycle 1. If iyang input is 1 as stated here, kung iyang output. So we don't know because iyang present output is dependent sa previous na input. So wala man takabalo unsa ang previous nga input. It's either 1 or 0 man. So that's why gigray lang ni siya dire. Kaya wala takabalo, no? Honestly, wala takabalo. If it is high already, no? So iyang output is of course low. Low. Sorry. Di ba din siya inverter? Iyang output is high. If iyang previous na input is low, iyang current na output is low. So, pwedeng ana. But tungod kay wala takabaloan it's best na i-ignore na lang nato. Don't know. So, how about for the second cycle? No? For the second cycle, the output at the second cycle, transfer lang ako sa silong ang mga cycle numbers. Yung output sa second cycle is based on the previous state. No? So si D flip-flop is naka-store siya og state from the first cycle, which is high. No? That's why high ang output sa second cycle. How about sa third cycle? Third cycle is low because second cycle input is low. No? So malalagi ang gi-copy paste, no? Gi-move lang niya forward. No? Ideally nag-introduce lang siya og delay. No? So that's how the D flip-flop works, at least for the context of our learning microprocessor systems. So the next is based on the hierarchy. Supposed to be dirinta niyo kaninga statement. Dito sa speakers ng slide pero sige lang. Next is after the D flip-flop is the 1-bit register. So what is the component of the 1-bit register? It's just the D flip-flop. So the 1-bit register, 1-bit register's function or functionality or yung specification is right here. So input, it has now two possible, two input pins. The in pin and the load pin, and an output pin that you call out. So its function is maybe another term for the load na pin is an enable. Maybe sa mga books mo yung ginagamit nila nga term, enable. If load T is true, if load T is true or equal to 1, then output at T plus 1 is equal to the previous na input. If not, output is retained. Output is equal to the present output is equal to the earlier output. So malalanggit siya kung ano, the 1-bit register is designed if the D flip-flop is designed to introduce delay, the 1-bit register is designed to store 1 bit of information. So that 1 bit is either 1 or 0. So the DFF here introduces the delay. The 1 bit register stores the information then. No? So what's happening here? So we have two inputs, the actual information and the load pin, or the load pin. Okay. The 1 bit register stores and limits 1 bit value until instructed to load a new value. Okay. So one may tabo. No. For the first cycle, input is 1. No? Input is 1. The load input is also 1. So what is the output? We do not know. Again, because we do not know the previous state of our register. Now, how about for the second cycle? The second cycle, the load input is 2. Sorry, 0. So off. And the input is also off. The output is 1 because the previous output is 1. Notice, no? If load is 0, no, else, meaning load T equals 0, just like in cycle 2, output is the previous output. Sorry, it lang sa klasa. Yeah. So here, no. So second state, second cycle, the output now is high, no, because the previous output is high man. So third cycle, because the load is still 0, no, the load is still 0, even if the previous input is 0 or low, it will retain the same state, no? It will still retain the same state because 0 man ang atong load na terminal, no? Or load nga input. Okay? Now, what's interesting is the fourth na cycle. Sa fourth na cycle, actually later pa din, no? Okay. After pa may tabo, ang sa next na cycle after pa sa fourth na cycle, the moment na nag-high na pod ang load na terminal, no, or load na pin, okay, that will prompt the input to change state, no? Or store that state. So as for the fourth na cycle, si input na pin is low, no? Meaning sa fifth cycle, the output will copy that state low until mag-high na sad si cycle. Si load, si load, no? High na sad si load. So let's say ato ni extend, no? Additional cycle 6. High na pud ni dire, no? High na siya diha. Then low na pud speakers. Let's say si input is high na dire. High. Okay. Meaning on the 7th cycle, si output will become high. Yeah, i-retain lang man yapon niya, no? I-retain lang niya dire because wala man siya gitagang instruction to change state si input, no? So it will retain the low na state, no? Or sorry, low na output. Okay. So ahaya lang siya mag-change state. Notice ha, ahaya lang i-copy ni output ang input if nag-high ang load. Yan na lang, no? So dire sama nag-high si load during the first cycle, during the fourth cycle, and during the sa atong own nga sixth na cycle, no? Mga times nag-high sila. So during the times na mag-high ang load, ay lang mag-copy si output, no? So sa fourth cycle, meaning by the fifth cycle, gi-copy na ni output si input. Sa sixth cycle nag-high, so by the seventh cycle, i-copy na ni output si input. Okay? Is it clear? Klaro na ba? So the first thing that we need to notice is when mag-high ang load. Mas better siguro kung giname ni siya as enable, no? Enable na pin, but load enable, synonymous naman sa gina siya. So enable is as if na-turn on iyang capability to store that state for the next na cycle, no? So whenever the enable goes high, the output will copy the previous input. Yan na lang, no? So siguro better siguro to na to i-take note, no? When load goes high, output for next, okay, cycle will copy lang akong term, no? Para naman na siya sa pag-change of state, no? Will copy the output for the next cycle will copy the input of this cycle. Or pwede gyapon, the output for this cycle will copy the input of the previous cycle. No, either way, pareha naman. Synonymous na siya. Okay. So that's how the 1-bit register works. Any questions? None so far?